in this experiment, we are going to discuss about single phase transformer. Okay, so what are the objectives of this experiment? Number one, the basic principle and operation of the transformer. Number two is to experimentally determine the transformer polarities. Number three, to demonstrate the operating characteristic of the transformer and to demonstrate the impedance reflection and also to demonstrate the isolation of both sides of the transformer. Here is an example of a transformer and here is our transformer terminal using the lab board that we are going to use later. Okay, to begin with our discussion, we should know that the voltage across the inductor is equal to L multiplied by the rate of change of current with respect to time. So B is equal to L di dt, right? So B is the instantaneous voltage across the inductor, L is the inductance in Henry, di dt is the instantaneous rate, the current change amperes per second. Okay, let's be familiar with some terms in the transformer. What is transformer? Transformer is an electrical device designed on the basis of the concept of magnetic coupling. It uses magnetically coupled coils to transfer energy from one circuit to another by the principle of mutual inductance. Later on, I'm going to demonstrate to you what is that mutual inductance. Okay, what does it do? What does transformer do? Number one, voltage transformation. It can either step up or decrease or step down the voltage applied to the primary winding. Okay. Another use of transformer is for isolation. It can isolate the circuit load from the supply, keeping the same voltage level across the secondary. So in this case, there is no change in the voltage, right? The same voltage level, but the only purpose of the transformer is just to isolate. So isolate the circuit. This is the symbol for transformer. We have a transformer here, and we have another coil here. The same voltage, BP and BS, the same voltage. So the purpose only of this transformer is just to isolate. Impedance matching, practice of designing the input impedance of an electrical load or the output impedance of its corresponding signal sources to maximize the power transfer or minimize signal reflection of the load. So this is just almost similar to our topic before in our Circuits 1 lab, maximum power transfer, wherein we design the charger. Do you still remember? We have RTH, right? We have it should be equal to the load, right? In order to obtain what? Maximum power transfer. Okay? So the transformer impedance matching is also a very, very important application of the transformer. Now, let us go back to basic. The first law of electromagnetic induction of Michael Faraday states that whenever a conductor is placed in a varying, take note of this, varying magnetic field, an electromotive force is induced. If the conductor circuit is closed, a current is induced. As you can see here from this figure, we have here varying magnetic field, right? And this varying magnetic field is being induced in this coil, right? And this is a closed loop. There will be a current induced. This is the induced current. Look at this meter. It's changing, right, left and right, because there is a varying magnetic field, right? The second law of electromagnetic induction says that if a flux passes through a turn of coil of wire, a voltage will be induced in the turn of wires that is proportional to the rate of change in the flux with respect to time. So in equation, there will be a voltage induced in a turn of wire, which is N, right? That is directly proportional to the rate of change of the flux with respect to time, right? So B is equal to N, number of turns, dphi over dt, right? This is the equation for the induced voltage. Now, let me just give you an introduction on how a transformer works. As you can see here, we have a generator. Our source is what? Our source is an AC signal. It's an AC signal. Wait, let me just erase all. Our source is an AC signal. An AC signal, right? We have a generator. It has a north pole, and the rotating magnet here has a north pole and south pole. It means and it is rotating. It means to say that it is giving a magnetic flux, a changing magnitude of magnetic flux. Let us have it played for you. Okay, now it's rotating. So the magnetic flux is changing here. The magnetic flux is changing, right? Okay, and look at the other side of magnetic flux. It is inducing voltage on the other coil, right? Okay, so there will be induced voltage because there is a magnetic flux that passes into a coil as per the definition of Michael Faraday. So the free electrons here will be traveling. As you know, there is an electron. If there is an electron flow, there is a current flow, right? So this is the current. Okay, let's pause for that. What if, let's go back. Let's pause on here. So here, we have a changing voltage, right? The polarity of the voltage is changing with a certain frequency. And the magnetic flux here is changing. So the magnetic flux produced on this coil is it's being induced. It is being passes through this coil, right? The magnetic flux produced on this winding passes through this coil. Therefore, if there is a changing magnetic flux passing to the coil, there will be an induced electromotive force here on this 2 point here. So if there is an induced electromotive force, it is a closed circuit. There will be an induced current. Okay. What if the source is a battery? What is the source? What if the source is the battery? Is there any induced voltage here? Let's see. Okay, we have a battery here. As you can see, there is no induced voltage. Why? Because there will only be induced voltage if there is a varying magnetic flux. As in this case, it's a DC. The magnetic flux is not varying, right? This magnetic flux is not varying. This is constant. So there will be no induced voltage on this terminal. Okay? But we can also do something in this part of the circuit in order to have a varying magnetic flux here, right? What are we going to do on the battery source so that we can have a varying source here? So let's continue. So here, as you can see, there will be varying flux if we put a switch here, switch on, switch off, right? Switch on, switch off here. This is a switch. So the current flux will be available, flux will not be available, available and not available. So it's varying. So if that is the case, there will be some induced voltage on this portion of the circuit, right? But it's not the same as the intensity of that induced voltage is not the same as in AC, because AC it's rotating very fast. Here we need to operate a switch, and here also we are applying 18 volts and 9 volts alternately, right? Look at the operation of the switch. From here, 9, 18, a varying voltage. So there will be some induced, but it's not as constant the output induced voltage here is not as stable as in the AC source, right? Okay, so now let's go to another slide. Okay, so now you already have the idea of how a transformer works, right? So now let us go to let us try to understand what is magnetically coupled circuits. What is a magnetically coupled circuits? Let's start with a conductively coupled circuit. The circuit that we have considered so far may be regarded as conductive coupled because one loop directly affects the neighboring loop through the current induction. So you can see on this figure, we have this part of the circuit, and this circuit is directly affected. It directly affects the current here, right? If we have a Bs of t as the frequency increases, the impedance here will increase and the current here will change. It will affect this source current. So if this current is increasing, this will affect this current and this current also. So it is directly coupled, right? It directly affects through the it's direct contact. Now, when the loops with or without contacts between them affects each other through the magnetic field generated by one of them, they are said to be magnetically coupled. So again, when the loops with or without contacts between them affect each other through the magnetic field generated by one of them, they are said to be magnetically coupled. So here is an example of non-contact magnetically coupled, right? So it is coupled by this P12. The secondary here is coupled by P12. What about this? This is application of the auto transformer, right? This is an auto transformer. This is a special case, special topic in auto transformers. See, we will have a very long here, long winding. This of course, it's obviously this is a step down. Okay, here there will be some magnetic flux, and it will affect the flux of the secondary. But let us just focus to non-contact or without contact. This is our topic for today. So we have here the number of turns on the primary. We have the number of turns in the secondary. And let me see. Let's go to another slide. So if you still remember in physics, right? What is whenever there is a wire that has a current, the direction of the magnetic field is can be represented by the right hand rule, right? This is your wire. The current direction is on this from left to right. So if you hold this, your thumb will show the current direction, and the other finger, the four fingers, will show the magnetic flux direction. So if we apply it here, I have this current. The magnetic flux is on this direction, right? And if it passes through a coil here, so this is a coil, so many wires, and there will be the intensity of magnetic flux will be increased, right? Okay. So again, if a flux passes through a turn of coil, voltage will be induced in the turn of wire. That is directly proportional to what? The rate of change of the flux, which is also as described, as I defined earlier. But the flux induced by the current, so that but the flux is induced by the current I, so that the change in flux is caused by the change in the current. So what does it mean? We have the flux is changing by the intensity of the current. So the current is changing with respect to time, right? Di. So we have here the flux is changing with respect to the current, and the current is changing with respect to time. Okay? So we have N. We can just rewrite this equation. B is equal to N, d flux, dphi over di, multiplied by di over dt. Right? So You still remember at the beginning, what is B? The induced voltage is equal to L di over dt, right? L di dt. Now notice, comparing these two equations, we have here di dt. We have here di dt. This is voltage. This induced voltage. This induced voltage. It means to say that L, this L, is equal to N dv over di. So we have L is equal to N dv over di. This inductance, L, is commonly called self-inductance because it relates the voltage induced in a coil by time-varying current in the same coil, right? That's why it is self-inductance, because it is inducing voltage in the same coil. Okay? What about mutual inductance? Mutual inductance. Now consider the two coils with self-inductances and that are in close proximity. Take note of this. It's close proximity with each other. So we have this. We have a current source. We have this current. We have magnetic flux on this direction, right? On the positive cycle, and then negative cycle, it is changing, right? The positive cycle, negative cycle. Let's say from here, positive cycle, the flux direction is here, right? It's on this counterclockwise, and when the negative cycle of the source, it will become the magnetic flux will be on the other rotation, so the current will be reverse, right? So, but anyway, since there will be a changing magnetic flux, there will be an induced voltage. So, this flux, that the magnetic flux emanating from coil 1 has two components, which is P11, which links only the coil 1, and P12, which links only the which links both the coils, right? Coil 1 and coil 2. So since there is a link on the other coil, there will be an induced EMF which is equal to B2, right? Now, although the coils are physically separated, they are said to be magnetically coupled since the entire flux P1 links coil 1. The voltage induced in coil 1 is V1 will be N dP1 over dt, right? V1 is equal to N dP1 over dt. This is V1, right? Now, only flux P12 links the coil 2 so that the voltage induced in coil 2 will be equal to V2 multiplied by N dP12 over dt, right? dP12 over dt. So this will be V2. Okay? Again, as the fluxes are caused by the current flowing in coil 1, it can be written as, we can also again rewrite, since this flux P1 is changing with respect to the current, dP1 over di1. So this one here is the L1, is the self-inductance of this circuit. What about B2? B2 can be written as N2 dP12 over di1, right? Because this flux is with respect to the value of di1, and di1 multiplied by di1 over dt is equal to, we can call this M21 dP1 di1 over dt. What is M21? M21 is the mutual inductance of the coil with respect to 1. So M21 is the mutual inductance of the coil with respect to 1. So we have V1 and V2, right? Okay, now suppose we put the source on the other side. So what will happen? We will have P2, right? P2 will be equal to P21 plus P22, right? P22 will produce a self-inductance on this part of the circuit, right? And P21 will generate an induced voltage which is equal to B1, right? So B2 is equal to N2 dP2 over dt. We can write as N2 dP2 over di2, because di2 now, this is the source, di2 here, right? And multiplied by di2 over dt. So this part of the equation is called L2, right? L2, L2 multiplied by di2 over dt. This is called the self-inductance of coil 2. So we can write here, we have in the beginning, we have L1, we have L2, the self-inductance of coil 1 and coil 2. What about B1? B1 is the number of turns of N1 multiplied by dp21 over d2 over dt, which we can rewrite this as N1 dp21 over di2 multiplied by di2 over dt. So we can write this as M12, right? This is the mutual inductance, the mutual inductance of coil 1 with respect to coil 2, right? So we have M12. Incidentally, M12 is equal to M21. So remove the subscript, we can just call it M, mutual inductance of the transformer, right? Now, let us now have some familiar with the parts of the transformer. So this is the transformer, this is BP and BS. By the way, this transformer, I can also use this as BP, I can use this as BS. How can I use it as BS? How can you use it as BP? Okay, here's the trick. If the source is connected here, let's say I will use BG as a source. If I connect the source here, this portion will become BP and this will become BS, right? However, if the source BG is connected on this point, on this side, this will become the BP, this will become the BS. What does it mean? BP is the primary voltage where what? Source is connected. Okay? BS is the secondary voltage where the what? Load is connected. To make it short, BP is the source side, BS is the load side. That's it. So NP is the number of primary windings, NS is the number of secondary windings, Phi is the flux, circulating flux. Okay? So we have here, right? In the beginning, we have two coils in front of each other, right? Now we have put a core. This is square. This is a core, right? What is the purpose of this core? A core is a higher permeable materials which describe the material's ability to carry flux, right? The core improves the magnetic coupling between the primary and secondary. So this is used for improvement by providing low reluctance. Reluctance is the opposition offered in the magnetic circuit to a magnetic flux. So it's just like a resistance. Reluctance is to resist the flux, the flow of the flux, right? So to improve the flux, the movement of the flux, we have to use a transformer core. Okay? And this is the symbol, schematic symbol for transformer. And this one is also a schematic symbol for transformer, but this is used for building electrical plant. This is to transformer, right? Why? Okay? So if you see this BP, BS, this is used in the electrical plant, in buildings, this transformer. Okay, let us have again define the parts of the transformer. Primary side, the input side, usually the source is connected. Secondary side, the output side, usually the load is connected, right? So for the secondary side, we can have BS subscript and IS, the current. For the primary, we have BP, IP. What about low voltage side? What does it mean in high voltage side? Low voltage side is the side where the low voltage terminal are located. It can be primary or secondary. High voltage side is the side where the high voltage terminal are located. It can be primary and it can also be secondary. Now, let us focus on the number of turns. As you can see here from this figure, there are less number of turns compared to this side here. There are more number of turns. So obviously, this transformer if the source is connected here, BG is connected here, this is used as a step-up transformer, right? Now, the same transformer is this one. But in this case, I have to connect BG in this part of on the left side, across this terminal where there are more winding. So this is used as a step down, right? Step down. So I have the same transformer. I connected the source here. It is a step up. I connected the source here. It will become step down. So where is the, at this transformer? This is the low voltage side. This is the high voltage side. In this transformer here, this is the high voltage side and this is the low voltage side. Okay? What is the relationship of the power in the primary side and the secondary side? Now, let us first talk about ideal transformer. Ideal transformer, we are neglecting all the losses in the transformer. It means to say that the power in the primary is equal to the power in the secondary. And the power is, you know that it is multiplication of E, voltage times current, right? Voltage times current. But in practical transformer, there is no practical transformer that there is no loss. There should be a losses. So, okay? So the equation is P primary minus P loss, P core loss, and P copper loss equal to the P secondary. So how are we going to relate that in this transformer? Here, this is the power in transformer. Minus the P core loss, there will be losses on this core, right? Because of the reluctance, it resists the flow of the flux, right? There will be loss in the voltage here, power loss in the core. What else? P copper loss. What is P copper loss? P copper loss is due to the wire. As you can see, this is a winding, right? This is a winding. This is a long wire, right? So it is directly the longer the wire, the higher the resistance. Okay, if the resistance is higher, there will be a voltage drop, right? It depends on the cross-sectional area of the winding cable or the winding coil that you use, the magnet wire. Okay, so anyway, even though we are not going to talk about power loss, core loss, we're not going to consider that in our analysis. Let me just give you just some background, a short background of what are those losses. So in a real transformer, consists of a real transformer, an actual transformer consists of iron loss and core losses. The iron loss, this is the iron loss and copper losses. The iron loss, what are those iron losses? Core loss or iron loss? It is due to hysteresis loss in the transformer and eddy current loss. It has two types, hysteresis loss and eddy current loss. Hysteresis loss is due to the reversal of magnetism in the transformer, right? In the transformer core. So we have a transformer core here. The flux is going clockwise, counterclockwise. There will be some losses. It can cause heat. Eddy current loss, some parts of the flux gets in link with the other conducting parts of the transformer, because transformer, you cannot assemble transformer without any other conducting parts. So that circulating parts also, the flux will try to be linked on that metallic part. So there will be some circulation of current on them, and it will dissipate heat. So this is also have a loss. Right? And we also have now, number 2 is the copper loss, as I've said earlier, due to the wire, the winding itself, this one, right? We have a wire, the resistance is equal to the resistivity, rho, multiplied by L over cross-sectional area A, right? The resistivity in ohm meter, the unit here is ohm meter, and here cross-sectional area in meter square. Right, the length it is in meter. So we will have the resistance, the remaining. So let us go to the again. So we will consider ideal transformer, power primary BP multiplied by IP equal to BS multiplied by IS, the power across the secondary. Now, Now let us discuss about the dot notation, right? So we all know that the right-hand rule, if this is the current direction is there, the magnetic flux is in this direction. So look at this figure here, right? Look at, this is the voltage, positive voltage. Look at this dot. Okay, if I'm going during positive cycle, that this is the current direction. The magnetic flux is in counterclockwise, right? Okay, so it reverses when the input source is on the negative cycle. So there is a changing magnetic flux here. So it means to say, look at the current direction. When the current is going there, and this current is is going to the right, and they are the same direction. It means that this transformer has same polarity, right? It has same polarity. Okay, how does the polarity of the transformer has become opposite? It depends on the winding. Look at the winding here. It's entering from this point, and look at the output side. It is from this point, right? This is if you have a winding that is entering from the other side, that is reversed. That will be reversed. So let us have a clarification on that. So we have here an AC input. The current direction is from left to right, right? Here is also current direction are the same. They are said to be, they are in same polarity. Okay? And here, this is an example of opposite polarity. Look at the winding here. It's entered from this side, right? This winding. And look at the other winding. The winding is entered from the other side. So it will have reverse. But if you have a real transformer, before you use a transformer, you have to test your transformer. You have to know what is the polarity. So in order to know the polarity, we have to apply the dot notation. That is the importance of dot notation. Okay. As I've said, if they have the same polarity, we can say that the dots are connected here. Okay? So they have the same position of the dot. Both of the dots are in this point. Okay? Just put a dot here and here. We can say that they are they are the same polarity. But if the dot is here and the other dot is here, they are in opposite polarity. How to apply this dot? How to apply this dot to analyze the transformer? Let me give you an example. Right. So remember that if the dots are here, the same dot, they are the same polarity. We have, look at this connection. We have here BP. This portion here is BP. This portion here is BS, right? So I can say that BP, if the absolute value of BP minus BS is less than BP, right? If the value of B is less than BP, that means they are the same polarity, right? The same polarity. If the value of BS, if the value of B is greater than BP, they have opposite polarity, because this here, that means you're going to measure this voltage from here, right? Let us derive the equation. Let's say, let me erase everything. So here in this position, let's say we don't know this, we did not put this one first, right? Imagine that there is no dot here. We don't know the dot. This is the source. So whatever the polarity source will be followed by the primary. So it's positive here, negative here, right? And here, we don't know. Okay, let us apply the Kirchhoff voltage law on this transformer. I have connected this wire. From this, I have to take the loop here, right? Let us write the voltage equation, minus B. And this is negative and positive on BP, minus BP. Okay, and here, we don't know the polarity. But if the reading here will give me plus BS, will be equal to 0, right? And here we have B is equal to minus BP plus BS. It means there is the difference. And you take the absolute value of this, and which is less than BP, it means to say that they have the same polarity. So we have the same polarity. That means the dot is here and the dot is here. Okay? Suppose here in this condition, they have this different polarity. What will be the reading in B? B is the voltage between this terminal and this terminal. Let us derive the equation here. Minus B, right? This is the source, suppose positive here, negative here. Minus BP, right? If the dot is here, that means this will be negative and this will be positive. Minus BS will be equal to 0. So B will be equal to negative BP minus BS. Take the absolute value. Of course, if you take the absolute value, the value of B will be greater than BP. Right? The value of B will be greater than BP. So it means to say that your transformer had opposite polarity. Right? What will happen if you use the transformer with opposite polarity? You can see here the waveform, right? If you are, they are opposite, they are out of phase by 180 degrees, right? Like here, this is our transformer. We don't know the polarity. So what I should do, practically, I have to connect a wire from here. And I had to input here, I had to put here a voltage, right? This is my BP. Let's say this is, will follow the polarity of my BP. And here, we don't know that this is BS, because we will know only the polarity of the secondary according to the output reading on B. On B here, we have to measure the voltage here. This is your positive, negative. Again, we will take the loop. Okay, so it's minus B, minus BP. So this one will appear whatever if you will have plus BS will be equal to 0. Of course, you will, when you measure the voltage here, you will just check what is the value of the voltage. If the value of the voltage here is less than BP, that means they have the same polarity. Okay? This is to simplify the analysis. If the value of B is less than BP, they have the same polarity. Next, here, if the value of B is greater than BP, they have opposite polarity. Okay? As simple as that. Okay, now, let us now try to discuss some mathematical analysis on the transformer. So, we have P primary is equal to BP times IP is equal to BS times IS, right? The voltage and currents of the transformer are related by what? Turn ratio. So, turn ratio, we have NS, secondary turn ratio, number of turns in the secondary and the number of turns in the primary. We have the turn ratio. NS over NP is equal to N, which is also equal to BS over BP, right? So, we take the reciprocal BP over BS is equal to NP over NS will be equal to IS over IP, which is equal to 1 over N, the reciprocal, okay? So from this equation, we can say that BS is equal to N multiplied by BP and IS is equal to IP divided by N, right? IS is equal to IP divided by N. These are the relationship. Okay. So, to simplify, for you to easily remember, BP over BS also, the turn ratio is primary, and divided by the secondary turn ratio, you will have the reciprocal 1 over N. Right? And IS here, except the voltage and the number of turns are the same. What I mean is, they are both, the primary are both in numerator, and the secondary side are the denominator. So it will be equal to 1 over N. But for IS, for the current, it should be opposite, IS or IP. Okay? Voltage and the number of turn, primary over secondary. But the current is secondary over primary. It should be equal to the reciprocal 1 over N. So now, this can be applied in the reflected impedance. The importance of the turn ratio is in the reflected impedance. What is reflected impedance? Is the equivalent impedance load you would have to connect across the primary voltage in order to produce same value of current that would flow in the primary transformer due to the load connected to the secondary, also called impedance reflection. So how do we apply impedance reflection? As simple as this. Guys, listen. Let's say here, let's analyze this problem. If BP over BS is if the transformer rating BP over BS is equal to 380 over 220, determine the magnitude and phase of the current IP from this given circuit. So we have this impedance 1100 ohm plus J1100. They are in series. Let us simplify this impedance. It's equal to, in polar form, 1556 angle 45 degrees. This impedance can be reflected into the other side, into the primary side, by applying the turn ratio, right? So what are we going to do? We had to divide. So set load over N squared, right? Set load over N squared. This is our set load. This is our set load. So to calculate, N is equal to BS over BP is equal to 220 over 380, 0.579. So IP, what is the current IP? IP here. IP. Oh, let us go for the equivalent circuit here. This will be 380, the source. This is now our reflected impedance of the secondary, right? So it will be 1556 angle 45 over N squared. So we can calculate IP will be equal to voltage divided by impedance, right? So voltage over impedance is equal to 380 angle 0 divided by this reflected impedance 1556 angle 45 divided by 0.579 squared is equal to 0.082 angle negative 45. That will be what? The current IP, right? So again, let us try to repeat. What did we do? We reflect this impedance to the other side. After that, we draw the equivalent circuit. When we draw the equivalent circuit, we can calculate using Ohm's law, we can calculate the current. IP is equal to 380 over set in. Okay? As simple as that. We don't need to complicate things, right? Just remember, the set in is equal to set L over N squared. Now, is it possible? Is it possible to reflect the input impedance into the secondary side? Right? Is it possible? Let us have this example. Now, in this case, we have a voltage rating of BP over BS. So we can get the N, right? We can get the N. But in this question, the actual voltage, input voltage is 100 only. So 100, angle 15. Now, first thing that we should do is determine the reflected impedance of the primary into the secondary. How to do that? In this case, we have to multiply by N squared. Right? Set reflected of the primary will be equal to N squared ZP. Right? Set of the primary multiplied by N squared. What is the impedance of the primary? It's equal to 316 angle 18.14. So, let us now calculate set reflected, 0.5 squared, and 316, we have a reflected impedance of 79 angle 18.4, right? Now, after that, we can rewrite this. We can simplify our circuit, right? Oh, what is the question number 1? This is for question number 1. Determine the reflected impedance. So, this is the reflected impedance. So, what is question number 2? If the actual voltage is 100, if the actual voltage BS, the secondary is 100 volts, right? Secondary is 100 volts. Calculate the magnitude. That means you need to, if you want to redraw the circuit. Do we have a space here? Okay, redraw the circuit. This is your source. And this will now be your reflected impedance. And then your impedance of the load. Right? This is this impedance of the load, this load. So this is the reflected, the set reflected that we calculate, this one here. So this is now 100 angle 15, right? 100 angle 15. So we can calculate IS will be equal to BS over the total impedance, this one plus this impedance, this is set L, this is our set L, this combined here, set L. So we will have BS is equal to set rep reflected plus set L, will have IS here equal to 61.287, 61.5 angle 28.7 degrees. Okay? So, question number 3, calculate the magnitude and phase of the primary. So, we have BS, 100 divided by N, we have the primary. Right? 200 angle 15. What is IP? What is IP? Just multiplied by the turn ratio. So, 0.5 multiplied by 61.5, 61.5, the value that we got from here, right? And we will have the current IP. If we have the IP, what is the total input voltage? Because the question here, question number 3, calculate the magnitude and phase of the primary voltage BP and the voltage BT. We have the primary already, we have here. And BT is what? Set PIP plus BP. Okay, we have BP. So how did we analyze that solution? We have BP plus the voltage across this primary impedance will be equal to BT, right? So how you calculate the voltage here? We have to multiply this impedance with IP. So we have set PIP plus BP will have B impedance. B total, right? B total here is 208.3, angle 16.42. Okay? Now, let us go to our experiment. In our experiment, we don't know the dot. Let's say this is our transformer. We don't know the polarity. We are going to use 380, 220. So 380 here. This is the 220. This is a multi-tap transformer. Okay, if I took the output from here, I will have 220. So let us have to know, we have to know the dot, right? We have to know the dot of this transformer. It means to say, let us say we have to put 380 here, connect 380. And from here, we have to connect a wire, jumper wire here, right? And we will measure B, and we will measure it, the voltage here, plus or minus. How are we going to do that? We are going to do that experimentally, right? Let us know. Let us have a test. Let us go to our lab bolt. Let us go to our lab bolt now. Opening for you. Now I assign, this is my lab bolt. This is the transformer, resistive load, inductive load. In the beginning, we will just analyze the dot of this transformer. This is a 3-phase transformer here, but we are going to use only one of them, right? We are going to use one of them. So we are going to provide 380 source voltage. A source voltage, wait. Okay. Source is 380. Okay. So this one is off. Our lab volt. And then here we have to put here. Okay. And another one here. I'm going to put here. This is 380. Right? And I'm going to put a jumper wire from this point up to this point, right? This is the jumper wire, and I will have, of course, a voltmeter, this voltmeter here to measure the input here, okay, which is 380, and actually we don't need to measure, we just need to measure the BP directly. What is BP? We measure here BP, right? We just measure BP. Okay? So now, let's make it 380. And then switch on the data acquisition. Now it's green. Now let us try to switch on the power. Okay? What is our voltage E1? Voltage E1 is giving us, repress, 170 volts. So B is 170 volts. It means to say it's less than BP. So what does it mean? This transformer has the same polarity, right? The same polarity, right? So Let us try to check our lab module. Okay, in this part you're going to test if you put it here and get the voltage. So let us try to do this part. We are done with this part, right? We know that this is the dot are on this point. So what about this? Let us try to apply this method also. So you have to put here. Okay, let me, the difference here is just delete this one. Okay, switch off. Okay, wait. Switch off first. Delete this. So the jumper wire, sorry. This jumper wire has to be connected on the down side, right? I had to connect the downside here as from the lab module. From the here at the bottom, I have to connect here. So from here now I have EB here, and the other one must be connected here, right? Okay. Now let us try to simulate now. Open. Okay. It means to say 600, right? That means the dot is not there. 600, it's greater than BP. So meaning to say it add together, that means the dot here is, we go to our first test, the result of our first test. That means we are testing similar transformer, right? It means to say that the dot is here, because when we put here, we are assuming that the dot is here, and that is here, right? No, wait. Okay, we know that the dot is here already, and the dot is here, right? So it means to say, when we connect it here, it gives us a higher value, right? If we give us a higher value, because if we took if you take the KBL here, KBL. If you take the KBL, let us have the KBL. How are we going to? We will have KBL like this loop, right? It will be minus B minus BP, and then it will give me minus BS will be equal to 0. That means B is equal to the absolute value of minus BP minus BS. So it will be greater than BP, right? So that means the dot is really here. To confirmation. Here we already proved that the dot is in the location. That here is to double check that really the dot is on this position. Okay. What's next? Okay. In this slide here. Okay. So we can set test 1. What is B? We have to write the value. We have the value. I think in test 1 we have around 170, right? 170. Let's say here test 1 170. What is BP? BP is 380. BS is 220, right? BS plus BP and BS minus BP. So we have here the result here 170. Here we have test number 2. B we have 610, 600, we have 600, right? 600 volts. So 380 also, 220. Okay, BS just add together and just take the subtract. Now let us go on this part of the circuit. Let's go on this part of the circuit. Okay, let us try to go to this connection, other connection. We have here, this is an example connection, it's assembled. Okay, we have here, this is our transformer here, and connected to 380. So how did I connect it on the, I just want to explain to you how did I connect it. I have 380 voltage source going to the to 2200 ohm, and I had to measure the IP, which is I'm going to use the ammeter. I can put the ammeter here, or I can put the ammeter here. It will give me the same value. So from the source, right, 380 from here going to the ammeter, I1 positive and I1 negative, going to the 2200 ohm resistance. As you can see, this this one here is connected, it's switched on 2200, and it is in series with the inductive load, and again 2200, and after that it will go to the primary of the transformer, right? Primary of the transformer, and then it will go back to the source from here, go back to the source. So from here, negative, going back to the source here, right? Going back to the source. So what about this yellow wire? This yellow wire is to measure the voltage across BP. So it's going here E1 positive and E1 negative going to the other side. Now let us go to the secondary. In the secondary, we have an ammeter here to measure IS. So from the secondary, I use the green wire going to the I2 positive and I2 negative going to the resistive load. So I2 negative going to resistive load 1100 and a capacitive load minus J1100. So this one is a resistive load going to a series with capacitor, and the other side is going back to the BS. So this other side here, the capacitor, other side of the capacitor is going to the BS, right? And we need to measure the voltage across BS, so we need to connect this to the E2 positive and E2 negative. So this is how I connected, I simulated, and then I have the value, right? B primary is 233, and secondary is 134. That means to say I have a 380 input here. There is a voltage drop. I have a 380 input here. There is a voltage drop on this impedances, and the voltage across this terminal between this point and this point, BP is 233.3. And the voltage across here at the secondary is 134. And I have the current IP that's flowing here. This is IP, and this is IS. What is the power for the primary? We have 13.27 watts and 8.18 watts in the secondary, right? So how are we going to connect that? Let us try again in our lab module, in our lab bolt. So here we had to connect it going to the I1 positive and I1 negative into this input 380, and then from here, not here first. We need to go first to the resistance. So let's delete this one. Let's delete. Okay. So from here, negative into the resistance, right? So I have to switch on this. It's 2200, and from here to the inductive load, and from here going to the primary, and the other side here will go back to the 5, right? Okay, and of course we need to measure the voltages, the primary. Okay, wait, why is it all white? Okay, we have to measure from here primary. Okay, we have to measure the primary, right? And what about in the secondary? Let me show the circuit. This is our circuit. We have there 1100 and J minus capacitor and resistor. So from here, which 220, we have to go to what? We have to go to the I1. It's white. Let me remove this one. Delete. So you need to red one. Okay, from here to I2 positive, I2 negative into another resistive load, and switch on 1100 and go to the capacitive load here and switch on 1100 and go back to the other side of the secondary. And also, of course, we need to measure the voltage, right? So we need E2 to measure the voltage here, and from here we have to measure the voltage. Okay, we have measured the voltage, and we need to switch on, and then simulate, check the values. Okay, why there's no values? I think we are disconnected from, I need to reset the lock. Yeah, okay. Now I need to put on this one, and this one is on now. Verify that it's green, and then simulate. So we have here, this is the B primary, B secondary, I primary, I secondary, and we have the power and this power. Okay, so now what's the next part? So here on this part we have only 380, and we have very simple two impedances, which you can do this one. And also here we need to connect the source 220 to the other side. So it means to say that your transformer, where's your transformer here? Transformer, this will be the source connected here. It will be connected here, and the output will be connected there, just like here. Right? The source here, and we have here two sources, two impedances. So where is that? So let's do it in okay. In this case, we will use let's switch off first. If you want to switch off, this will be our source, so this will be 220, right? 220 is around here. Let's see. We will adjust later. So we will have 220. We can connect it here, but we will not connect there. Let's see the drawing. So we will have or directly there, and there is no impedance, so direct. So we will have here directly connected here. Okay, we are not measuring the current. We need to measure the current. So we will just go from here, going to I1 positive and I1 negative into here, and we will put 220 from here going there. And our load is what? Is a series combination of 1100 and J1100 minus J1100. So from here we will measure also the current, right? We'll measure the current from here, and from here to resistive load. So we need to select 1100, switch on, switch off, and from here going to capacitor in series, right? This one, and we need to change this one, J1100, and from here it should go to this one, right? So go back there, and we will measure now the voltages. We will measure the voltage to measure the primary. This is now the primary side, right? This is the primary side now. I will have to put it here, positive, E1, and I need to connect the E2. Let us connect E2. Let's adjust this. Yeah, E2 into this voltage here, right? Okay, and we can simulate. You can open this one and simulate. Right? We have here 187,319. So we need to increase this to 220. Right? 220. Increase it to 220. Yeah, now it's 220 now. 220, let's see. Yeah, I adjust this to 220. 375 is the output, right? Of this, the secondary now is 370. So we step up the transformer. Okay, we step up the transformer, and look at what happened here. We have a total power in this low voltage side is 86, and the total power in the high voltage side is 64. So because there are losses in the inside the transformer. Okay? So in your lab report, you need to do the same, and you have to do this one also. Okay? So actually in this part, we only have three, how many connections? 1, 2, 3, 4. You have to do 4 connections, right? Before we are doing this also, that's why I have here, you can do also, when we are in face to face, we are going to do all of this circuit also. So how to do this circuit? Okay, how to do this circuit? Which this is I'm going to do it in practical in front of you. Okay, this is just let us do this one if you want. Okay, let's do this one. Anyway, since at this moment it's not required, so I will not show it. We can show it in our class. Okay. So your lab report, take the screenshot of your connection, take the metering, and write the conclusion, and fill up all the tables.